Mhm. What is coming here? Just give me a minute. Yeah, comes on everyone. Able to see the screen, right? Great. Great. So last class we have finished with the gravitation. Today we'll be starting with Gauss law. So this is a little bit of a different chapter, meaning at least in terms of problem solving, right? You will see there are a few numericals and there are problems, where it is mostly you need to prove things with statements like because of this, it looks like this, and therefore this is the answer. Meaning questions would be of that sort. That's what makes this chapter a little, I won't say tough, but it is a little different. So unlike other chapters where you just put equations and everything, here it is a little different. So we'll see that. So Gauss law. So the first thing we define is something called electric flux. The symbol is phi. So electric flux is defined as flux is proportional to the number of field lines passing through an area. So if more field lines pass through an area, we say there is more flux. So straightforward definition, it is simply depends on number of field lines. That means if I have area like this, if I have a bigger area and if I have a bigger area, and let's say field lines are like this. Let's say there are 5 field lines here. Here also there are 5 field lines which are perpendicular to the surface. Let's say there are 6 field lines coming out and 1 field line going like this. Now, if you actually check this out, they have same flux. So flux, right, if you see, it only depends on number of lines. It doesn't depend how the lines are entering the surface. It doesn't depend how big the area is. It doesn't depend. See, there are 5 lines here. There are 5 lines here. There are 6 lines coming out and 1 line going in. So 6 minus 1 is still 5. So flux is simply how many lines per unit, how many lines are passing through an area. So that is the definition of a flux. Now, mathematically, if you want to calculate this, flux is given by integral E bar dot dA bar, where E bar is your electric field. A bar is your area vector. And if E bar is constant, it comes out of the integral. And your flux becomes E bar dot A bar, which is EA cos theta. That means if you have a loop like this, and if you have field like this is your area vector. Area vector is perpendicular to the plane. Hope you remember from vectors A cross B. A cross B gives you the area of a vector which is perpendicular to the plane. This is there. Now, if you notice something here, doesn't it look like I'm just contradicting myself? Just now I said flux does not depend on angle, does not depend on area, and suddenly I'm saying flux depends on area and angle. What is the catch? All have same flux. So the thing is, let me ask you this definition. What is field exactly? If you remember, we defined field like this. Field is nothing but number of lines per unit area. Remember that? If you have more lines per unit area, we say the field intensity is more. Suppose if I had field lines like this, if you remember, we say field here at point A is more than field at point B. So field is nothing but proportional to number of lines per unit area. So what is flux now? Flux is integral E dot dA, and field is number of lines by area. Area will cancel. You'll get number of lines now. So there is no contradiction as such. So the thing is, electric field and electric field lines are not same. Electric field lines per unit area is called field. So if we study in terms of, so if we study flux in terms of field lines, then flux is independent of, then flux won't depend on the area and the angle. You just count the number of lines and you're done. But if we study in terms of electric field, then flux depends on area and angle. So be careful, both are not contradictory as such. It all depends on how you're studying them. So there's only one formula that we did so far. So this is your main thing. So we're just going to play with this formula for today. You can just note it down if you want. So flux is simply integral E bar dot dA. E is the field and A is the area vector. It's a dot product. So the thing is, the Gauss law, we give importance because Gauss law came before Coulomb's law. Coulomb's law is actually more powerful. The Gauss law has its own advantages. But Coulomb's law end of there is more powerful. So we will try to do it in the reverse. We will take Coulomb's law and from there we'll try to prove Gauss law and then we'll go ahead. Clear with this? So great. Now integral E dot dA, E bar will be given. Now problem is A bar, how will you take the area vector direction? Now for closed figures, and this is something we discussed first time in vectors. For closed figures, we have normals inside and outside. We take outward normals as positive. So if you have a sphere or if you have a cube, so the area vector is along the normal. So here for a cube, there are 6 faces: perpendicular, 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 and perpendicular. So whenever someone gives you a closed figure, we take the outward normals as positive. Means if the lines are coming out, then the flux is positive. The lines are going in, flux is negative. And for open surfaces, means if it's not a closed figure, you can actually choose any direction you want, but we prefer to keep the angle acute. We choose A bar towards Z bar. It is just a convention. So if you give me a disk, now I can take area vector right side or left side, but let's say field is this way. So just for convenience to keep the angle acute or to keep the flux positive, we'll always choose area vector in the direction of E bar. You could have taken the other direction also. There's no issue as such. So for closed surfaces, it is fixed. We'll take the outward normals. But for open surfaces, we choose you can choose anything. Clear with this, everyone? Clear? Let's see a question on this. Others, do keep your cams adjusted. I can't see your faces, some of you. Make sure your faces are visible on the screen. The idea. Let's see a question. So we got a cube here. This is your x-axis, this is your y-axis, and this is your z-axis. It's a cube of side A. So we will name this thing as this is phase 1, phase 2, phase 3, phase 4, phase 5, and phase 6. You're getting what are the phases? 4 is the floor, 3 is the ceiling, 6 is the xy plane, and 5 is this guy. 5 is this outside one. I hope you're able to see the 6 surfaces. Now, if the electric field is E naught into I cap, a constant field. Second question, if the electric field is E naught x into I cap, so field is changing with x coordinate. Third question, if electric field is E naught x I cap, so there's a component of field changing along x-axis, E naught yj cap changing in y-axis, E naught zk cap changing in z-axis. Three different questions. Find the flux on each phase. Meaning, this is the question, say, if the field is E naught I cap, find the flux on phase 1, phase 2, phase 3, phase 4, phase 5, phase 6. If the field is E naught x I cap, find the flux on 1, 2, 3, 4, 5, 6. So there are like 18 questions here. Let's start with the first one. Easy stuff. Let's get the first one is easy. Try, give it a minute, and then I'll show you. Then you can do the second and third. Again, remember, the only formula I taught you is integral E dot dA. That's it. I didn't teach you anything else today. Let me show you. Look at the first one. The field is E naught I cap. So first, how is the area vector? So the area vectors are outward normal. So this is the area vector, area vector, area vector, area vector, area vector, and area vector. So these are the area vectors. How is the field? Field is E naught I cap. So here the field is this way. E bar, E bar. You can see this is perpendicular. E bar, this is perpendicular. E bar. So 4 ke liye it is perpendicular. E bar 6 ke liye it is perpendicular, and this is E bar. So there, straightforward. So flux will be on 2 nahi. 3, 4, 5, and 6. All these 4 are 0 since the field is perpendicular to A bar. Flux on 1 will be minus E dot A. So angle is 180 degrees. Flux on 2 will be EA. A is nothing but small a square. It's a square plate. Easy. Getting what we did? You took each phase, you found the area vector, you found the field, and just do E dot A. And 3, 4, 5, 6 will be 0 because there is no, the area vector is perpendicular. All clear with this? You want an answer, you can type in the chat box to this one. I think my host and co-host got messed up. Now, can you do the B part? Same thing. Now, instead of field being constant, now it is E naught x I cap. The field is changing with x coordinate. Now what? Try. I'll give you a minute. If you got B part, then C part will come. So in the exam, if I have to ask you, I'll ask you the C part directly. नहीं रे Puruj. That's not the answer. By 2 आएगा नहीं. The E naught xi cap will look scary, but think carefully. There's no need to integrate anything here. That E naught xi cap is just to scare you. There's no need to integrate. Try. I'll give you another 30, 40 seconds and I'll show you. Let me help you see. On phase 1, let me ask you this. On phase 1, is x coordinate changing? What is the x coordinate on phase 1? Phase 1 is along yz plane, isn't it? X is 0. Field है ही नहीं. You getting my point? So for a given yz plane, x coordinate is constant. Now try. See, story is the same. So the area vector for this guy will be this way. Area vector. Now, interestingly, when the field is changing, it is perpendicular. So the field is actually changing for 3, 4, 5, 6. But it is always perpendicular. And here E will be 0, and here E will be E naught into AI cap. Can you see that thing? Field at 2 is not 0. On this plane, what is the x coordinate? Isn't that entire plane as an x coordinate x is equal to A? So if you look at this entire plane here, this entire plane is x is equal to A. It's constant. So flux on 3, 4, 5, and 6 is 0 because E is perpendicular to A. So I agree, E is changing, but it is always perpendicular, so it won't matter. Flux on 1 is 0 because E itself is 0. Flux on 2 is E naught A I cap. So field is actually constant on the plane dot A square I cap. So this is E naught A cubed. Is this making sense, everyone? So the thing is, the moment you see E naught X I cap, you need to ask yourself on a given surface, is E changing or not? Now, E is changing on 3, 4, 5, 6. But it is always perpendicular to the area vector, so it always becomes 0. Is this clear, everyone? Now, using the same logic, can you do the third part? Now it is changing E naught Xi cap, Y cap, J cap, Z cap. Now, once you see this, people will think like, oh, what the hell, field is changing in all directions. How will you approach this? Try, I'll give you a minute. Yeah, right, Vihan. Try others. Give you a minute more. Yeah, since it's a scalar quantity, you can find flux only for E naught Xi cap, then find flux only due to E naught by J cap, then only find flux due to E naught J cap, and then add all of them. Don't take all the three fields at the same time. Take one field at a time, find the flux on each surface, and just add them up. That is more easy for you to observe. Let's see. So let's say this is E naught X I cap. Let's take flux 1, flux 2, 3, 4, 5, and 6. So this is 1, 2, 3, 4, 5, and 6. Then I'll take E naught Y J cap. Then I'll take E naught Z K cap. So I'll find all the 6 fluxes and just add them up. Yeah, I think like I told today, host and ghost got mixed up. So send it here if you have any answers. So E naught Xi cap, this thing we calculated, this guy will be 0 because E is 0. Flux 2 will be E naught A cube 0, 0, 0, 0. Now when I say E naught Y J cap, main field is going up now. Now who is perpendicular? 1, 5, 2, 6 are perpendicular, isn't it? So same thing with X, it will be on the Y. So 1, 2, 5, and 6 will be 0. 4 will be 0, and this guy will be E naught A cube. E naught Z में 1 will be 0, 2 will be 0, 3 will be 0, 4 will be 0, 6 will be 0, and this will be E naught A cube. Check. So you're done. So flux in 1, flux in 4, flux in 6 will be 0, 2, 3, and 5 will be E naught A cube. That's the total flux passing through each phase. Any doubts on this? So you take E naught Xi, E naught Y, E naught J separately and then find the flux and then add them up. Any doubts on this? Anyone not convinced with this? Please ask me. Clear, na, Viknajit? Sharman? Nikhil? Clear with this? Ishana? Daksha? Clear? Falak? Puroja? Next one? Arush? Go ahead. Next one. Let's say we have an incline. It's a square plate. Side is A. This is making an angle theta like this, meaning look at this thing. If you look at my screen, this is how it looks. So if you look at my phone, right, this is like an incline like this. So you're getting how it is, and this is making an angle theta. So side view will simply look like a straight line. It's like a block sliding on an incline. So this is a square plate of side A. And in this region, you have a field which is E naught x I cap. This starting point is your origin 0, 0. Find the flux on the plate. I hope you're able to visualize how is the plate, right? It's like an incline. So it's making an angle theta with the horizontal. The field is E naught x I cap. Find the flux on the plate. Now it matters. The field is changing with x coordinate. Try. You got a minute more. Daria, question is clear with this? Daria, question is clear?
Yes, sir.
Okay. No, your screen is going blank. Do check it out. There are three things you have to be careful while solving that question. Let's see. Nah, that's not the answer, Goroja. Think. I'll give you a minute and then I'll show you. How will you choose an element? How will you find the flux on the element? And how will you take the limits? These are the three things you need to think. How are you guys getting sine 2 theta? Look at this. At a distance x, you could take a small dx. This is the element you're talking about. Again, I'm exaggerating the element. It will be very small. This length will be how much? This will be dx by cos theta. And this will be, if you look at the side view, this is dx. This is theta. So this slanting length here is dx by cos theta. Are you getting it? So area vector is not a into dx. Therefore, the element dA will be a into dx by cos theta. That is one mistake people do. That's the first thing you have to be careful. So when you take a thin slice, the area will be into this slanting length. That is one. Second thing, when you take field here, this is your area vector dA bar. This is the field vector E bar. So if this is angle theta, this angle is 90 minus theta. Therefore, the small flux will be E into dA into cos 90 minus theta. Angle between the E bar and A bar is not theta, it is 90 minus theta. This is the second thing you have to be careful. Now, therefore, flux will be integral E dA sine theta. What are the limits? What is the x coordinate here? This x coordinate is a cos theta, na? X is not going from 0 to a. X is going from 0 to a cos theta. So the limits will be 0 to a cos theta. Is that making sense, everyone? Because the plate is at an incline, when you drop the perpendicular, x coordinate is only a cos theta. That's the third mistake people do. So there are the three things you have to be careful: the area vector, the limits, and the angle between them. And then you are done. So this guy will be E is E naught x, dA is a dx, and that's sine theta. So sine theta only. Integral 0 to a cos theta. This will be E naught a tan theta x square by 2. Limits will go from 0 to a cos theta. Substitute the values there. You will end up with E naught a cube by 2 tan theta cos square theta. You can write sine theta by cos theta. So one sine, one cos will go off. Yeah, but you can simplify. Clear with this? You have to be careful. How are you taking your element? How are you taking the angle and everything? Any doubts on this? Clear na Parth? Jainil? Ojas? Kritik? Clear. Next one. Turn in the page. Any doubts? We have a hemisphere. Of radius r. We have field E here. Constant field. Find the flux passing through the curved surface. And I want you to find the flux on this shaded surface, green one. No, you need to ask yourself, Janil, can you? What is the proof? Yeah, some of you did get it. Now, can someone tell me what is wrong with this? Can I say flux is equal to field into area? Surface area is 2 pi r square. What do you guys think about this? This is a blunder. You know why? Can someone tell me why there is a blunder? Cancels out, nah. Yeah, right, Poroja. Angle changes. So if you look at this thing here, at every instant, look at the area vector here. This is the area vector, area vector, area vector, area vector. And if you look at the field here, field is like this, E bar, E bar, E bar. So if you look at this, the angle changes every time. So when you say flux is equal to integral E dA cos theta, that cos theta won't come out of the integral. You can't solve this directly. So you can't say directly E into 2 pi r square. That's a blunder. Be careful. Because flux is not E into area. It is E into dA cos theta, the integral. And how do we solve this? We have our favorite concept, projected area, if you remember. Now, not only this thing, you take any random amoeba surface like this, right? Can I make a statement like this? If I draw the field lines, you can draw like this also. Now, look at this line. Huh? This line is entering and this line is leaving. So this thing will cancel out anyway, isn't it? That line isn't useless. You entered and you left. So can I simply say the number of lines entering the curved surface is equal to the number of lines leaving the disk? The number of lines entering the curved surface, there are 5 entering, 1 is leaving here, and remaining 4 are leaving here. So the total flux entering the curved surface is equal to the total flux leaving from the disk. So for simplicity, let's keep it simple now. Something like this. Now it is easy to see. So we can clearly see. And what is the flux cut definition? That is a whole definition of flux. The number of lines passing through an area is flux. We observe the number of lines quite an important concept. You should check out fluid mechanics. This will come at least 6 times. The projected area and projected length. So number of lines passing through curved surface and the shaded area is same. Therefore, flux is given by, simply we call it E into projected area. And what is the definition of projected area? An area which when you put there, it becomes a closed figure basically. By introducing this green color area, the whole figure becomes closed. So coming back to our problem, so if you have taken an hemisphere, if you have taken a cone, if you have taken an amoeba shape, it doesn't matter. So for all of them, the projected area is same. The flux will be simply E into pi r square. Is this clear, everyone? So the moment I introduce that red color area, this whole figure becomes closed. So that is the definition of projected area. The first time you saw this thing was in fluid mechanics. Clear? Easy one, but it's a proper mains level question.
So
Vihan.
So like in that, like the first drawing that you made, like, so what counts as entering the area and what counts as like not? Because like technically speaking, the other arrow also leave, right?
What are you talking about? Area vectors will be like this. So this is entering and this is leaving. You don't know the meaning of entering a room and leaving a room. You're saying both are entering the room only. Both are leaving the room only. You entered a surface. Tell me one thing. How do you enter inside?
Hmm.
You entered, right? And if you keep going straight, you left. What is the problem?
Okay.
What do you think entering
Okay.
and leaving is? So according to you, you should come like this and leave like this only, sir.
No, so but then couldn't we like at that point where it was entering and leaving, couldn't we define a new projected area over there?
Don't complex yourself so much. Keep it simple. You want to introduce new area vector and everything. If you are going opposite to area vector, you are entering. If you are going
Okay.
with the area vector, you are leaving. Keep it simple. Happy?
Yes.
Yeah. Don't confuse yourself with so many things. You understood? Keep it that way. Next thing. A better thing would have been should ask like, what do you mean by like, exactly how do you know something is entering and leaving? And then you go with the area vector definition. If you go with the area vector, you're leaving. If you are going opposite area, you're entering. That I hope explains. Next thing, suppose if you have a disk. Radius r. Always, meaning this is what I always believe. Keep your terminologies as simple as possible. The more complex terms you start introducing, exam you'll just get confused. Exam will be such a tense environment, right? If I ask you 2 plus 3, you will think of 2 times. Is it 5 or 6? And if you go there with so much baggage, right, things will be pretty messed up. There, we have a point charge here, Q, making an angle theta with the disk, and radius is R. So this point charge will give field lines. Means flux is entering the disk. Find the flux passing through the disk. Quite a good question. You should definitely mug up the result. But let's see how to do this thing. Try. There are two ways that we can do this at least. I'll show you both. But first you try for 2 minutes. Think how can we approach this? How do we approach this, Parth? Parth, you must have got some ideas. Come on, let's try. Focus.
We will integrate.
Yeah, right, Parth. How do we integrate? That is the question, right? Chalo, let's get an element and start integrating then. Yeah, but true. That's the first thing you need to figure out, boss. There is an integration involved. Then once you realize integration is involved, what is the first thing you need to do? You need to find how will you take an element. Find the flux on the element and then integrate all the elements. Story looks easy to say. Only when you put it on a paper, you'll realize what the hell. Try. When you take a disk, how do you choose an element? Do you guys know that? This is one thing I keep telling you. In physics, right? Luckily, you have very limited amount of shapes. I can even tell you, right? Disk, cone, hollow cone, solid sphere, hollow hemisphere, infinite line, or line. बस हो गया. Arc. I think yeah, बस इतना ही shapes था. मतलब if you say. So for every shape, if you know how to choose an element, I think then you'll always get an idea how to do. So for a disk, how do you choose an element? We take a thin rings. Yeah, most of you got it right. You take a thin ring here like this, whose radius is x, and whose thickness is dx. So this is your point charge q. So from here, how is the field? The field is along the charge. So this is the field vector. And how is the area vector? Area vector is this way, dA bar. There. Now try. I gave you how the element looks. So there is an angle between each ring and each field, and so theta bhi change ho raha hai. So let's call this angle alpha, and so this will be alpha. There. Daksha, what is D? What is E?
The E is the epsilon.
Okay, what is D?
So D is the distance of the charge from the center.
When did I give you? See, show me where is D in the equation. There is one theta and there is one R. That's it. Where are you bringing D from? Now what? Try. I'll give you a minute. Now, mostly if you have figured out till here, right? Technically, physics part is done. This is always the headache in physics. Integration in physics, right, is always about choosing an element and getting those distances and everything, angles. And then the integration is actually the easier part. So what is area vector dA? 2 pi x circumference into thickness. So what is the flux on this thin ring? Field E, dA, and the angle is cos alpha. What is E? K Q by R square. 2 pi x dx cos alpha. So if you extend this line here, this thing is D. Remember D, I didn't, I need to find that. This distance is smaller, the hypotenuse. I'll just write it again. So this is R, this is alpha, this is D, and this is X. Perfect. So this guy, let's simplify. K will be 1 by 4 pi epsilon Q, and R will be, now see, D is actually constant. So I'll get everything in terms of D. So we have cos alpha is equal to D by R. So R will be D secant alpha. So this guy will be D square, sec square alpha, and this guy will be 2 pi. And what is X here? Tan alpha is X by D. So we have X is equal to D tan alpha. If you differentiate this, you'll get dx is equal to D tan alpha ka differential is D sec square alpha D alpha. So I'll just dump everything here. So this guy will be 2 pi D tan alpha. And dx will be D secant square alpha. D alpha and cos alpha. Then I brought everything in alphas. And then, yeah, the D's will cancel off. You can clearly see this guy and this guy and this guy goes off. I eliminated D from the picture. 1 pi also goes off. I get Q by 2 epsilon. Secant square alpha will also cancel off. There is one tan alpha and there is one cos alpha. So that is sine alpha by cos alpha. That will cancel off. You will ending only with sine alpha d alpha. There, life becomes so easy. And therefore, the flux will be Q by 2 epsilon integral sine alpha d alpha. Limits will go from 0 to theta. Because at the center here, alpha is 0. If you go to the topmost point, alpha is theta. That is what is given. Integrate this, you'll get cos theta, which is Q by 2 epsilon. Cos 0 is not 0. Be careful. 1 minus cos theta. There, that's your flux through the disk. Pretty good result. You should definitely mark this up. So flux through the disk is given by Q by 2 epsilon 1 minus cos theta. As long as the theta is same, it doesn't matter how big the disk is. Have a look at the integration. You could have eliminated alpha, brought everything in terms of x and integrated. The story will be the same. Now, how do you integrate that? Max will take care of it. But the thing is, if you should have got till here, if you got till here, then physics is done. You can either eliminate X and bring everything in alpha, or eliminate alpha, bring everything in X. You can play around either way. This much integration, you should be comfortable. Advanced, this is like okay integration, matlab, yeah. And if you actually see, is the integration really tough? It is simply integral sine alpha. Integration is not tough. The headache was getting till there. This is one way to do brute force integration there. Now there is another way to do this. Clear with this? Check out the integration. Any doubts on this? Let's see. The alternate. So when you take this disk here, when you take the charge q here, so I will assume this belongs to a part of a circle where plus q is at the center. This was the disk. You can clearly see here every line that passes through that disk will pass through that curved surface, isn't it? If you make it this is a part of a sphere, every line that passes through the disk will pass through that part of a sphere. Plus q is at the center. Therefore, you can clearly see here the flux passing through the disk is equal to the flux passing through the part of the sphere or the curved surface. So if I can find flux on this curved surface, so this would be the center of that thing. Means if I had extended this, this would have been a full sphere. Is this making sense, everyone? And do you guys remember what is the area of that piece? Do you guys remember what is the area of that piece? Multiple times I told you. First time you saw where? In calculus. 2 pi r square 1 minus cos theta. याद आया? Second time you saw in friction. Angle of repose. Dust is sprinkled on a thing, find the area covered in dust. This is the third time you're seeing. You will see this again in optics. You will see this again in modern physics. You will see this multiple times. So remember that result. So this shaded area here, 2 pi r square 1 minus cos theta. You can check out the integration page 110 calculus. This was beginning, 11th starting maybe did this sum coming like this. Okay, fair enough. So what is the catch about this? So from here, if you look at any point here, the area vector dA will be this way and the field also will be this way. So you can clearly see E bar is parallel to dA bar at all points. Because the charge is at the center, the field is along the normal, area vector is along the normal. Therefore, the flux will be integral E bar dot dA, which is E dA cos 0. E will be how much? Q by 4 pi r square. Sorry, Q by 4 pi epsilon r square and dA. So this will be Q by 4 pi epsilon r square into integral dA. And dA is nothing but area of that piece. Q by 4 pi epsilon r square into 2 pi r square 1 minus cos theta. And therefore, you'll get flux is equal to Q by 2 epsilon 1 minus cos theta. It is the same thing, solid angle only. I'm not using the word solid angle, but what is solid angle ka definition? Solid angle is defined as this area which is there. This thing is called the solid angle. Solid angle is defined as the surface area by r square. You're getting it? So if I ask you find the area of that, so you actually have to use integration to find the surface area in the first place. You're getting it? So the solid angle for this part will be 2 pi r square 1 minus cos theta by r square. Yeah, but again, I don't want to use this, meaning solid angle as such is not really that useful for us. But because in order to find the solid angle, you will actually find that area. If you already know the area, why to struggle with all this?
So,
Getting it?
so we don't know the distance between the charge at the center of the
Solid
disk.
angle doesn't care about the distance. कहाँ पे आया? R square तो R square cancel हो गया.
Okay, sir.
Did the final answer has R inside in it? No, no.
Yes, sir. Okay.
Yeah, so shouldn't be a problem. All clear with this? Now, can someone tell me what is the difference between this? Suppose integral dA bar and integral dA mod of dA bar. So for a sphere, what is the answer for these two? For a sphere, if I ask you what is integral dA bar and integral mod dA bar, what is the answer? The first one is 0. Why? Look at the area vector. So the area vector dA bar looks like a ball of spikes. So for every one vector, there's another vector which will cancel out. Second one, you're integrating mod dA means you're literally adding each and every part, you get surface area. Are you clear with this? So integral dA bar is different from integral mod dA bar. So here what we integrated is a scalar dA. We didn't integrate dA bar. So be careful with that. A little thing, but yeah, you should know the difference. That mod will change the whole answer. Is this clear, everyone? The alternate one. Any doubts on this? The result is important. The flux is q by 2 epsilon 1 minus cos theta. So let's see a question based on this. Let's say we have two charges, q1 and a charge minus q2. There'll be a lot of field lines between them, but there's one particular field line which is leaving at an angle alpha and enters minus q2 at an angle beta. So there are a lot of field lines, but this is one specific field line. So a field line leaves at angle alpha plus q1 and enters minus q2 at angle beta. Find relation between alpha and beta. How will you do this? These are the kind of questions when you see for the first time, you feel like, what the hell? How do you approach? Chenil, what are you even talking? The kind of statement you're saying. What is V here? Tell me. What is V1 and V2? Chalo, according to your logic.
No, like from the electric field, we can find the acceleration.
ठीक है. What is, you'll find acceleration of the electric field lines.
No, not the field lines. But like assuming a particle is placed, we can
Oh, where did you
try.
study that? I thought didn't teach you this.
So,
Where did I teach you that? And what is the speed of a field line? Speed of light. So what are you talking about?
okay. So it won't.
Yeah, Ishana got it. Yeah, this thing you should have seen once. So listen to this thing. It's okay if you don't get it. Don't, create blunders. When you say V1 cos alpha is equal to V2 cos beta, what are you talking? That's the kinematics, right? You're not projecting any particle. Where is gravity here? So you're saying if because of the gravity, the field lines will start bending? Just imagine how weird it looks. I put a plus q charge in presence of a gravity, meaning the field lines will start going like this. Nahin, na? Then. So here, listen. So the logic here is we'll go very, very close to the charge. So you take a disk very close to the charge. Again, I'm exaggerating. This very close meaning it's literally touching the charge. Similarly, take a charge very, very close to this minus q2. So consider a disk. Very close to the charge. Now, by symmetry, you can say there'll be one more field line here. This angle also will be alpha. This is also alpha. This is beta. This is also beta. Can you clearly see here? Every line that passes this first disk will cross the second disk. So can I say the flux passing through both the disks is same? The number of lines passing through both the disks is same. Therefore, so the flux due to Q1 must be equal to flux due to Q2. Therefore, they have same flux. So you should know the previous question ka result. So the flux will be Q1 by 2 epsilon 1 minus cos alpha. This is Q2. We are just checking the magnitude. So Q2 by epsilon 1 minus cos beta. 2 epsilon will cancel and cos alpha will be 2 sine square alpha by 2. This will be Q2 into 2 sine square beta by 2. That's your relation between alpha and beta. Yeah. If you can't take like this, if you take this far, then this angle won't be alpha, na? You're getting it? Suppose see. The lines are going like this. So ye angle alpha, where? Because of the tangent, na? This tangent makes alpha. If you take a disk here, this will be alpha. I don't know this angle. So you need to get it very close to it. And luckily, right, the flux does not depend on how close you keep. It depends only on the angle. So when you keep it very close, I can assume this thing is almost a tangent. That was a thing. Now, this question might look easy to solve. That is because you already know this result, isn't it? If you don't know this result, you can't solve this question. So technically speaking, 4 and 5 are related. If you know the fourth result, then 5 looks easy. Clear with this thing. It's a good one. Any doubts on this? Yeah. Let's see one more. Meaning, Daksha, that is the meaning of flux is same, right? So there's nothing called conservation here. Conservation means that only, na? Initial flux is equal to final flux. So kind of you're saying something like that, but there is no word like that.
Yes, sir.
Next thing. Suppose if you take a sphere, radius r, and you kept a charge cube at the center. Find the flux passing through the sphere. Let's get this. This is easy. See? So from the center, if you take any point, this is the direction of field, and this is also the direction of area vector. They're always parallel. E bar is parallel to dA bar at all points. Just now we did for that. Therefore, flux will be integral E bar dot dA bar is E dA cos 0. E is nothing but Q by 4 pi epsilon r square into dA. This is Q by 4 pi epsilon r square into integral dA, and dA is nothing but 4 pi r square. We get Q by epsilon. This you must have studied. Many of you have done already Gauss law. The flux inside a closed surface is Q by epsilon. So, but you'll notice something. This is independent of radius. Doesn't matter how big sphere you take, the flux is same. You can make even something better with this. So we are indirectly actually proving Gauss law now. So what this means is, now see, if you take a point charge Q here, and how will the field lines be? The field lines will be radial like this. Now, if you consider some random amoeba surface, and if you consider a sphere, isn't the number of lines same? It doesn't matter what kind of surface you take, the number of lines are same. That means the flux must be same. So flux through that sphere must be equal to flux through that curved surface, curved closed surface. This must be equal to Q by epsilon, since the number of lines are same. That's why it is important to know both the definitions. What is flux? Lines passing through an area. What is flux? Integral E dot dA. And you can keep playing with both of them. Because I don't know how to find flux on a curved surface, but I know how to find flux due to a sphere. Since the number of lines are same, flux must be same. So this gives you a statement here. So flux on a closed surface is given by the charge enclosed by epsilon. So indirectly we proved Gauss law with Coulomb's law. That means if you take any random surface here, and let's say this is Q1, this is minus Q2, and this is Q3, and someone asks you what is the flux inside, it is just Q1 minus Q2 plus Q3 by epsilon. I don't even care what kind of shape it is. Just take the total charge and divide by epsilon. Is this clear? So I know how to calculate for a sphere. I don't know how to calculate for any random amoeba shape. But again, going with the first definition, if the lines are same, flux is same, you can always argue and make them equal. Making sense? But what if the charge is outside then? So if you have some random amoeba surface here, and if you have a plus q charge outside, now what? You can clearly see for every field line, again, we have the same thing. So here the lines are entering inside, the lines are leaving from inside. You can read like that. So for every line that enters, there is a line which is leaving. Therefore, flux must be zero. That means if you keep a charge q outside, they don't contribute to any flux inside a closed surface. You're getting it? The number of lines are leaving is equal to number of lines entering. We
Yes,
can
sir.
see the number of lines entering and leaving are same. So entering, you're going inside. Leaving, you're going from inside to outside. Number of lines entering and leaving are same. Therefore, flux on a closed surface due to outside charges is zero. So if you're going to keep a charge outside, it is not going to contribute any flux. That means in the previous example that I gave you, if you had kept some charges here Q4 and if you had kept charge here minus Q5, the answer will still remain same. You're getting this? That is the reason. So outside charges don't contribute to any flux. Now here in the exam, they can ask a theoretical question like this. Listen to this question. A charge Q is placed on the outside of a closed surface. The flux at every point is zero. True or false? The total thing is different. The word is this. A charge Q is placed outside. The flux on the closed surface is how much? Zero. Charge Q is placed outside. Flux at a point is how much? Is it positive, negative, or zero? Both are completely two different words. So if you take flux at a point, now look at this. If you consider this point here, this will be dA bar. This will be the field vector. You can clearly see the angle between them is acute. So the charge will not have total flux. So therefore, flux is positive. If you look at this point here, this is dA bar. This is the field vector. Here, this angle is obtuse. So when the lines are entering, flux is negative. When the lines are leaving, flux is positive. Total is zero. So here, flux is negative. You can even take a case here where the line becomes a tangent. So when the line becomes a tangent, this angle becomes 90 degree. So at this point, flux is zero. So flux at a point can be positive, negative, or zero. But when you add all these fluxes, you'll get a zero there. Quite an important statement there. So be careful. Flux at a point is different from flux on a closed surface. These things, right, will come in a statement question. And I have seen people doing that, the charge Q is placed outside, find the flux at a point on a closed surface. People will not read the word at a point. They just remember one thing. Charge is outside, flux is zero. They'll mark it and come without thinking. You're getting it? So be careful. Flux at a point is different from flux on a closed surface. So if I have to write it mathematically, E bar dot dA need not be zero at all points. Some points it will be zero, not at all points. But the moment you say integral, if you put a circle there, means you're doing a full integral of a closed surface. This is zero. This is for full surface. I hope you're getting the meaning of that. At each point, it need not be zero, but when you add all of them, the total will be zero. So flux at a point and flux on a surface are two different things. Any doubts on this? Clear, everyone? There. So we know one thing now. If you put a charge Q inside a box, any random box, closed box, the flux is Q by epsilon. Let's say a question. So let's say we have a square plate here. Side A. From the center, someone kept a charge here plus Q perpendicular to the surface at a height A by 2. So this guy will send field lines through the square plate, find flux through the square plate. So we have a square plate, and from the center at a height A by 2, there is a charge Q. Find the flux passing through the square plate. There's no need to integrate here. Yeah, this is a standard one. Think. I'll give you a minute. If you've already done this before, it is easy. If you're not done for the first time, you need to think of it. So when you get these kind of questions, right, you need to ask yourself, why did I give that A by 2 specifically? On the side of the square is A. So when you see this, you will realize there's some kind of symmetry. So this is one chapter. Gauss law mein, we actually use a lot of symmetrical things. There is some kind of a symmetry, something like that. So listen to this thing. I'll give you an idea. So if you make a cube of side A, so let's make a closed box. And now you're going to put a charge Q here at the center. So this becomes the center. Now what is the flux in a closed surface? This is just now we studied Q by epsilon. You're getting it? Now, what is the use of that A by 2? Now you will see the use of A by 2. Now, because it is at the center, all the 6 faces are symmetrical. You're getting it? All 6 faces are symmetrical. And there are 6 faces, therefore, flux through the plate will be 1/6 of the cube. That's it, easy. Suppose if it is not A by 2 and let's say it is A by 3, then how can you do that? You can't do that. But you can still say flux through the cube is Q by epsilon. This statement is still valid. But because there's no symmetry, I don't know how much flux each one is contributing. Are you getting the difference? Because the charge Q is in the center, you can say it is symmetrical and solve. If instead of A by 2, if I give A by 3, I can still say flux in the cube is Q by epsilon, but I don't know how much each surface is contributing the flux. Is that making sense, everyone? Clear with this? Take a break. Come back by 7 o'clock. We'll continue from here. We'll see more variations of this cube ka thing. But any doubts so far, please ask me. Okay, come back in 10 minutes. Come back by 7. Yeah, let's go ahead. Same thing. Let's say if it is like this. So we have a cube here. Let's say this charge is at the corner. Let's name the surfaces. Let's call this thing 1, 2, 3, 4, 5, and 6 is the behind one. Find the flux passing through the cube. So if you keep the charge on the corner, how much is the flux on the cube and what is the flux on each face? Let's get this thing. This time instead of keeping it at the center, what if I keep it at the corner? How much is the total flux contributed by this charge in the cube? And how much each face will get? Others do keep your cams on. That's not the answer. How much is each face contributing? So imagine I make a big cube of side 2a. Now, if you try to draw the cube here, so this is that small cube, isn't it? And this charge q here is now at the center. So if you take a cube of side 2a, it will have 8 small cubes like this. So this flux on this big cube, now it is at the center. It is q by epsilon. This will be 8 times flux due to the small cubes, because there are 8 small cubes that you can fit in this thing. Therefore, the flux in that small cube is q by 8 epsilon. So if you keep a charge in the corner, it will contribute 1/8 of the flux. Is that clear, everyone? So what about the each phase then? Now there is something here. See, listen. Now if you look at this phase here, the charge q, when you kept at this corner, how will the field lines here? The field lines will be like this, isn't it? Can you see? The field lines will be parallel to the surface. If the field lines are parallel to the surface, that means the area vector is perpendicular. So any surface that touches the charge will have the field lines parallel to the surface. Is that making sense, everyone? So surfaces which touch the charge have field lines parallel to the surface. That means E becomes perpendicular to A. So in our cube here, Charge cube is touching here. This is 1, 2, 3, 4, 5, and 6. You can clearly see 3 is touching, 2 is touching, and 6 is also touching. So flux in 2, flux in 3, and flux in 6 is 0. And the remaining 3, flux 1, and flux 4, and flux 5, you see by symmetry, they'll all contribute equally. That will be 1/3 of the flux in the small cube. And flux in the small cube is q by 8 epsilon. So this is q by 24 epsilon. How will it strike? Meaning it's a 8 cube ka center it is. Daksha. Why are you talking as if it is new? That is because you're not revising the old stuff. You do so many complex things, and you shouldn't be asking this. How did we do this question? How did we do this question? Find the ratio of potential at the center and the corner of the cube. This is not the first time you're seeing this. You have seen this before. Electrostatics. Don't you remember this question? Square plate is there. Find the ratio of potential at the center and the corner. Find the ratio of potential at the center and the corner of the cube. There.
Yes, sir.
Clear with this, everyone? The corner will be, there'll be 8 cubes because that is always the center of a big cube. Same question. Let's make it even a little better. So the previous one would be like a proper mains level question. Find the flux on each face. Now, what if 1, 2, 3, 4, 5, and 6? Now, what you did, this charge cube which is there, you pushed it slightly towards the face center. So this is the face center. You pushed this charge from here to here, slightly, very small distance. Towards face center. To now find the flux on each face. Now how do you approach this? This would be the actual question in advance. Flux on each face, right? There are 6 faces. I want each face ka flux. 1, 2, 3, 4, 5, 6. How much will it be? How will you approach this one? Think. I'll give you a minute more. Let's see. Tell me one thing. If you move the charge very little, do surface 1, 4, 5, do they think something changed? They will still think the charge is at the corner, isn't it? So flux 1, flux 4, and flux 5 will still remain q by 24 epsilon. Since it is moved slightly, the distances will be almost same, the angles will be almost same. The three surfaces will think, yeah, this guy is still at the corner. So that is a use of saying moved slightly. Since it moved slightly, it looks like charge is still on the corner. For these three surfaces at least. So 1, 4, 5 are sorted. Flux on phase 2 will be 0. Why? The surface is touching the charge. If a charge touches the surface, the field lines are parallel. So that means the headache is the remaining two guys, 3 and 6 are the headache. Now look at this thing. So this cube which I got, let's say if I put one more cube like this, now where will the charge be? You have pushed it slightly inside, the charge will be here. Now tell me one thing, is this charge inside the closed surface or outside? It is inside. The total flux कितना होना चाहिए? Q by epsilon. Then how much will each cube contribute? So flux on each cube, because when you pushed it slightly inside, it will be Q by 2 epsilon. Is this making sense? From the corner, when you pushed it little inside, it is inside only, right now. If it is inside, the flux is Q by epsilon. Since the left and the right, both the cubes are symmetrical because it is on a face center toward on the face surface, so they'll contribute equal flux. Is this clear, everyone? Now the flux on the cube is nothing but flux due to 1, flux due to 2, flux due to 3, flux due to 4, flux due to 5, and flux due to 6. And this guy is q by 2 epsilon. 1, 4, 5 is q by 24 epsilon. Flux 2 is 0. Flux 3, I don't know. And you can see by symmetry, 3 and 6 are identical. Flux 3 is equal to flux 6 by symmetry. So when you move it on the diagonal, 3 and 6 will look same. So from here you can clearly see flux 3 plus, so this guy will be q by 2 epsilon minus q by 8 epsilon will be flux 3 plus flux 6. Therefore, flux 3 is equal to flux 6 is equal to 3q by 8 by 2, 3q by 16 epsilon. Take it out.
Sir, how did we say that flux of 3 is equal to flux of 6?
Okay, what do you think?
Did we say that by symmetry?
What did I write here?
Okay, sir.
I can understand people are hungry. होता है. Then 3 and 6 are symmetrical, right? Everyone agrees with that at least? वो तो दिख रहा है ना? When you're on the corner, 2, 3, 6 are symmetrical. When you pushed it towards 2, 3, and 6 are still symmetrical. This is what I was saying in the beginning of the chapter. Look at the question. There is no numericals, right? It's all arguments only. Because it is symmetrical, because it is like this, because it is like that, this is the flux. That's what makes this chapter a little different from others. It's all symmetries. Clear with this, Kritik? Daksha, got this? Dairya? Clear? Puroja, Ojas? Next one. Let's say we have the cube. This time you have an infinite line charge passing through one of the side. This is lambda. This is a cube of side L. This is 1, 2, 3, 4, 5, and 6. Find the flux in each face. Right, Vihan. We need to find what is the total flux in the cube. Now think, how will we make this symmetrical? Now listen, everyone, the whole question is this. Daksha, this is the idea there always. If you keep it outside or if you keep it on the, see, if you keep it outside, it is 0. If you keep it inside, cube epsilon. But the moment you keep it on the boundary, I don't know what to do, right? So you need to always think, somehow, can I make this thing go inside? I need to create a shape where this becomes the center of that whole new shape. That is how you should always think. So how to make this center of that new shape? And the shape should look symmetrical again. So for a corner, the center was when you have 7 more cubes, right? And for this guy, what will you do? Let's see. So how to make this the center of the cubes? Can I put 3 more cubes? I can introduce 1 cube here. I can introduce 1 cube here. I can introduce 1 cube here. Are you able to visualize? You will put 4 more cubes here, like, this surface, and this surface here. Are you able to visualize 4 plates on the top? So you will put a bunch of 3 more cubes. This was the red one is our initial cube. There I'm just painting 4 different colors. You can see that. My diagram is bad. So place 3 more cubes. So now this thing becomes the center of the thing. And what is the charge enclosed? So charge enclosed will be that line in the center, which is lambda into L. So this thing here, I'm marking with a more dark red. So this is the charge which got stuck inside. Na? So for the 4 cubes, the flux will be lambda L by epsilon. So the flux through each cube will be lambda L by 4 epsilon. This is the flux contribution due to each cube. Sure. And then just now we made a statement. If a charge passes through the edge, the field lines will be parallel to the surface. So here my infinite line charge is passing through 4 of them. See, so if you take this line charge here, You can clearly see the lines are parallel like this. The lines are touching here. So 1, 2, 3, 4, 5, and 6. So we're going to take this infinite line charge here. So you can clearly see the field lines are parallel to this. Field lines are parallel to 4. Similarly, field lines are parallel to 1 and 5 also. So flux in 1, 3, 4, 5 will be 0. E is perpendicular to A. So this is quite a useful thing. If the charge touches the surface, the field lines are parallel, discussion closed. So the remaining two guys, which is 2 and 6, will contribute half of the total flux, which is lambda L by 8 epsilon. Is this clear, everyone? And lambda L is the charge that is stuck between the four cubes. The dark red one, which I'm taking here, that is lambda L. Is this clear, everyone? So not only point charges, you can always introduce infinite line charges also. Any doubts on this? Anyone not clear with this, please ask me. Clear, Nanch? Nikhil? Soham? Vignajit? Clear, na, Falak? Niharika? Clear. Next one. Let's see one PYQ. There, this was advanced 2015 ka question. Try. An infinitely long line charge distribution of charge sigma lambda lies parallel to y-axis. There is a rectangular plate at a distance of root 3a by 2. Dimensions are given. Due to this line charge, so there will be field lines passing through this plate. Find the flux through the plate. Try. I'll give you 2 minutes. Let's see. So if you see the picture, right, this thing, again, you need to figure out, see, one thing, integration is not the way here. There's a symmetry there. The idea would have been here. If you look at this root 3 by 2 and this looks A, that gives you a feeling it looks like equilateral triangle height. And these things come with only experience. When you solve a lot of problems, you'll get the hang of this kind of stuff. You know, there's a symmetry. Even look at the option here. If you have to integrate, the answer doesn't look very bad. It looks a decent one. So, and so this infinite line charge will pass to the center. So, meaning, and how will the field lines look like? The field lines will look something like this. The field lines would look something of this sort. Isn't it? The field lines are going out radially in all directions. So if you look at the side view, so this was the center, the lambda line charge. So this was that plate. So I have to make this rectangular plate like this. And this is my argument here. Every field line that passes through this plate will pass through this surface here, curved surface. So every line that passes through this plate will be passing through this curved surface. Do you agree? And from here, if you look at this thing, this was root 3 a by 2 and this was a by 2, meaning this angle was 30 degrees and this angle was 30 degrees. You're done, right? Ask yourself, for a full sphere, for a full cylinder, what is the flux? For a full cylinder, the flux will be charge by epsilon and the charge will be lambda into L by epsilon. So for 360 degrees, you have lambda L by epsilon. For 60 degrees, how much flux you will have? 1/6 of it. Easy. So all these lines which will go from this charge here, they're going in all directions. So the total charge is lambda into length L. So the full cylinder would be lambda L by epsilon, but this green one is contributing for 60 degrees. Even if it is not root 3 a by 2, it could have still solved. If it is some other distance, then this would be like this. So basically the plate will be the chord of the cylinder. Then you find the new angle and then you do the same story. Is this clear, everyone? So the main idea there is you need to make it a chord inside a cylinder, the plate. So the front view would look like this. The side view, you can say. Is this making sense, everyone? So the picture would look something of this sort. This was that rectangular plate. This was that line charge. This was length L. So this charge Q was lambda into L. And the field lines are going away radially. So all the lines passed through this rectangular plate should be equal to this curve here. And that angle we proved it to be 60 degrees. That should be 1/6 of the total flux. Is the picture clear, everyone? It was an integer question. Clear? Next one. Any doubts on this? Let's say we have a square plate. Charged square plate of side A. Sigma is the surface charge density. Now from the center, you kept a plus Q charge at a height A by 2. Now, because both are positive, they will repel each other. Find the force between them. So this square plate, which is positive charge, and the point charge, which is also positive, both will repel each other. So there is a force between them. And how much is that? How do we do this? Listen. So there is a way to handle these kind of things. So one thing, we can't integrate and do that becomes very complex, but there is something we can do. We can manipulate the Gauss law to get something here, the flux one. Look at the idea, listen to this. So when you take this point charge Q here, so from here, take any random point, choose a small area here, let the charge be dq. The field will be this way, force, which will be field into dq. So this is the field due to plus q on the plate. Now similarly, if you choose one more point here, this also will be some force here. If you choose one point here, that also will be force here. Now you'll notice we have this horizontal components, so vertical components and horizontal components. Theta is changing, area is changing, everything is changing here. The horizontal components cancel out because it's a symmetrical shape. And how much is the force? I don't know, but one thing I'm sure, because of symmetry, for every horizontal force on the left side, there's another horizontal force on the right side. So horizontal components cancel out. So the net force on the plate will be only the summation of the vertical components, which is integral f cos theta. Agreed with this? Only f cos theta will add up and f sin theta cancel out. But what is f? F is nothing but field into dq. But what is dq? dq is nothing but charge into area. This will become E into dA into cos theta into sigma. So this is sigma, that is nothing but E bar dot dA. But what is E bar dot dA? Flux. So we have manipulated that equation to get a force. So the force on the plate will be sigma, the charge density, into flux due to the charge on the plate. And we can clearly see it is given A by 2. This question we have already done. So the flux will be Q by 6 epsilon. So this works when you know the flux. If you can't calculate the flux, you can't use this method. So there what we did, say, I don't know field, I don't know area, I don't know theta, but I know what is integral E dot dA. So we manipulated that equation to get a force. We have taken a random point, dq charge. We have taken a random field, E bar. Then we said only of cos theta add up. So this thing, right, you can more generalize it. If you take any random shape, and if you put a plus q charge here, I can do the same story here. So here you will get two forces, F vertical and F horizontal. Fx cannot be found. I need more data. But if you want to find Fy, you can use this thing. So Fy will be sigma into flux through that surface due to the point charge. Is this clear, everyone? So for symmetrical shapes, we know Fx is 0. If the shape is not symmetrical, Fx won't be 0. So I can't calculate the net force, but I can still find the vertical cone. Is this clear, everyone? These are some another type of questions based on flux. Now, if you try to do this normally using Coulomb's law, you will die. It's very complex integration. Like you take an element rod, and that rods will be finite rods. The distance is changing. Then you integrate the field. Yeah, it can be done, but lengthy. Clear with this? Let's see one more based on this. Suppose if you have a hemisphere with a closed disk. So let's say this hemisphere, this charge is plus q. This bottom plate is sigma. So you made a phi will be written in the plate as, yeah. See, the question is what? Phi is the flux due to the charge on the plate, right? So why do I care what is the charge on the plate? You're getting? So it's a hemisphere which is a closed with a disk on the other side. With a charged disk. Find the force between them. You're getting how is the question? So dome ka charge is plus q. The niche sheet is sigma. Radius is r. So I could find the charges. Find the force between the dome and the disk at the bottom. Again, remember the story is still the same, right? What is the force? Force will be sigma of the plate into flux due to that hemisphere or the dome on the plate or on the disk. Isn't that the formula? sigma of the plate we are finding into this. Now the catch is, how do you find the flux due to that guy? So this dome ka field, I don't know how it is coming, but some lines are going like this. So how do you find the flux? Right, Daksh, I think you got that part. You forgot a sigma. No, you got it. There is something interesting about that. This is easy there. See, if you take any point charge here, right? Look at this dome. Take any point charge here, small charge dq. So if you draw the lines from here to this corner, what is this angle? 90 degrees, right? That means due to this point charge, whatever field lines you are getting, all field lines that come due to this thing, 1/4 of the field lines will go through the disk, isn't it? So due to dq, 1/4 of all its field lines will pass through the disk. Now, this, from trigonometry or geometry, whatever in school you studied. So you take any point, all will make 90 degrees, isn't it? So any point on the dome will make 90 degrees with any diameter on the disk. That means all of them will contribute 1/4 of the flux. Therefore, the flux will be q by 4 epsilon. Therefore, force will be sigma into q by 4 epsilon. Is that making sense, everyone? You can take any point, right? You can take this point and this point, that is also 90. You can take this point and this point, that is also 90. So it doesn't matter which diameter you take. It will make 90 degrees with any diameter on the disk. So in any plane, 1/4 of the lines are passing. So the total flux must be 1/4 of the total flux. Is this clear, everyone? Clear? There, that is one neat one there. Any doubts on this? Because it's making 90 degrees. This angle is 90 degrees. So if you take a point charge q here, how are the field lines going? The field lines are going in all directions, right? 360 degrees may you have all field lines. So in this, if you come and tell me it's 90 degrees, so there shouldn't be 1/4 of the lines. Right, Arush? Yeah. There. So that is one. So we have done almost like 8 problems, especially this flux and everything. So make sure to go through the notes, right? And we'll catch up again on Tuesday as usual at same time. So any doubts, anything you can stay back and ask, or else you're free to leave. So, and the test will be online on Saturday as usual. Okay, with that we'll wrap up for the day. So if you have any doubts, you can stay back and ask, or else you're free to leave.